Hello, this is Magic 063 Differentiable Manifolds. I'm Dm Kchm, and this podcast is about product manifolds and induced vector bundles and some related things. So consider two manifolds M1 and M2, dimensions N1 and N2. There's a natural way to define a manifold structure on the Cartesian product set M1 cross M2 simply by taking the Cartesian product of charts. So this is pretty straightforward, but I'm going to do it. Suppose we have, that's an N1 by the way. Suppose we have charts like this for M1 and M2. Then it's an easy matter to just take the Cartesian product of those maps. I'm running out of space, let's go up there to R N1 plus N2. And you can check that the overlap maps are diffeomorphisms. One thing to watch is that, of course, in a product topological space or metric space, not every open set is a product of open sets, but every open set, or given an open set and given a point in it, there is a product open set that's a neighbourhood of that point and contained within the given open set. So it's certainly legitimate to have charts that are defined on open sets of that type. So there's no problem with that. It's easy to prove that the projection maps are smooth, and in fact they're surjective submersions. We still haven't said much about submersions, but these are very straightforward examples of submersions. We'll come to that later. And for that matter, injecting, say, M1 opposite a factor of M2 prime, a fixed point, or a chosen point there, gives a smooth map, and likewise for the other factor. So the question I want to think about is, what are the vector fields on this product manifold? And of course, you can take a vector field on M1 and a vector field on M2, and you can sort of take a Cartesian product of those on the product manifold, and that will be a vector field, but that certainly isn't enough. I mean, think of the example of R2. There's R2, and when we talk about a vector field on R2, it'll have two components. But each of those components will depend on both variables. So if I was to do this kind of thing in R2, I'd have x1 depending only on x and x2 depending only on y, and that would clearly be very special. And on R2 I might be able to get around that by multiplying by functions and so forth, but it might not be clear how to do the general case. So that's where we're headed, and we'll get an answer to that at the end of the podcast, and along the way we'll cover some stuff that's important in its own right and which we need for later on too. So the first thing we need to consider is pullback manifolds. And these are defined by situations where you have two smooth maps with the same target, both going into M0. And if we were just doing sets, we could say that the pullback of those two maps is the set of points in the product such that they project under the maps to the same point in M0. And the usual notation for that is there. Now, this situation occurs throughout manifold theory, lots of different places, and so this is one of the things that we would be covering in its own right. There's a standard condition which guarantees that the pullback is a manifold, and when I talk about a pullback being a manifold, I actually have in mind that it should be a good submanifold of the Cartesian product. And we haven't talked about submanifolds yet, but we will, and I'll make clear what I mean by a good submanifold in that situation. A regular submanifold or a closed embedded submanifold. So here's the standard condition. Maps F1 and F2 with the same target are said to be transversal if the tangent space at any point M0 to the target, where M0 is actually the value of F1 of something and F2 of something, is generated by the tangent space that's the image of M1 and the image of M2. So this is just an ordinary sum. It's not required to be a direct sum. These two spaces can certainly overlap, but when we take their sum, it ought to be the whole of the tangent space of M0 at that point M0. So transversality is one of those words that's used in several different senses, all of which are related, maybe closely or maybe only rather loosely, but this is one of the standard uses for transversality. So here's the theorem. If F1 and F2 with the same target are transversal, then this pullback set is actually a regular submanifold of the Cartesian product M1 cross M2. And in this case, we refer to it as a pullback manifold. The pullback manifold exists. And I'll come and talk about regular submanifolds in a future podcast. In particular, if either of the maps is a surjective submersion, then the transversality condition is satisfied. Submersion means that at each point of the domain, the tangent map is surjective. As a linear map, the tangent map from the tangent space at that point to the tangent space to the target at the corresponding point is a surjective linear map. That's what submersion means. There's an equivalent condition that we'll come to later on. So this happens a great deal. It's very common to have one map that's a surjective submersion, and that guarantees that the pullback manifold exists. So here's a little proposition, or perhaps even just a lemma, or perhaps even just a remark. Suppose that the pullback manifold does exist, and suppose that one of the maps is a surjective submersion. So I'm not actually assuming that the pullback exists because of a submersion condition. I'm just assuming that the pullback manifold exists, and in addition, I'm assuming that F1 is a surjective submersion. Then it follows that the opposite projection, just a projection of the pullback onto M2, is a surjective submersion. And you can get the idea of the proof of this just by looking at the set diagram. So in this diagram, just think about sets for the time being. We're assuming that this map here, no, I beg your pardon, this map here is surjective. And I claim that this map here is surjective. Well, how do I do that? I take a little point M2, I map it down to M0, and because F1 is surjective, there exists an M1 up here, which projects to M0. So M1 projects to M0, M2 projects to M0, so M1, M2 is in the pullback and projects to my given M2. So that's the complete proof in the setting of sets. And what's remarkable is that exactly the same proof works for submersion condition, so long as we do it on the level of the tangent spaces. And I'll just sketch this extremely briefly here, and we will come back to it later. But one thing about the transversality condition is that it ensures that the tangent spaces to the pullback manifold are the pullbacks of the tangent spaces. So I could put a tangent T in front of everything in this diagram, and I would have a commuting diagram of maps of vector spaces, and I'd be assuming that this map down here was surjective, because that's what submersion means, that the tangent map is surjective, and the same argument would go through exactly as before. And this is quite a powerful technique for working diagrammatically with manifolds. Anyway, the main thing at the moment is this little result and the transversality condition that guarantees the existence of the manifold structure. Now, having got this, we can consider the situation of a vector bundle on a base M and a smooth map into M. So this is like the pullback situation. F is a smooth map with target M, and E is a vector bundle, a rather special kind of map, but the projection has target M. And I'm going to produce a vector bundle, two different notations. F star of E, upper star of E is quite common. F shriek of E, F shriek E is also quite common. I'll use this notation most of the time because I want to keep the star for duals and certain other things. The shriek actually comes from bourbaki. It's been around for decades. It's less common than using the star, but it's certainly well established. So we'll go with the shriek. So I'm going to construct this vector bundle on M prime. And this construction is often described as pulling back the vector bundle E from M to M prime. Now, this word pullback, it's certainly a legitimate use of the word, but it's certainly confusing because there are so many other uses of the word. And indeed, I could have a little diagram of vector bundles, like our original diagram of manifolds. Each of these over a manifold M1, M0, and M2. And I could pose the question as to whether there's a pullback vector bundle structure. And that's a question that comes up, and it's a bit complicated, and I'm not going to do it, but I do want to mention that that's another legitimate use of the word pullback. So, in fact, I'll generally refer to these things as induced vector bundles. Another possibility is reciprocal image. It's a direct translation of the French. I think this was introduced by Dieudonné, who was effectively functioning as bourbaki as far as manifolds were concerned. But it's a bit unwieldy. So we'll stick with induced vector bundle. So I'm going to define the induced vector bundle structure on this pullback manifold. So my pullback manifold is here. It's M prime and E pulled back over M. The bundle projection is automatically a submersion, so the transversality condition is satisfied. And just for the moment, I'll write E prime for this pullback manifold. Then Q prime, which will turn out to be the bundle projection, is simply the projection onto the M prime factor. And therefore the fibre, that's to say the pre-image under Q prime of a point M prime, is just going to be the corresponding fibre of E, but with M prime attached. So usually there will be a large submanifold of points M prime which project to M. And each of those points will be attached to a copy of the same fibre of E. So the pullback vector bundle is made up of a lot of submanifolds, all of which are trivial vector bundles. We'll come back to that later. Okay, so this thing can certainly be identified with the vector space, and that gives it a vector space structure. So each of my E primes at each M prime has a vector space structure. Now I need to define the charts. I start off with a chart for E, and I do what's pretty well obvious. I'm going to define the chart for the induced vector bundle on the pullback of U alpha. So that's an open set in M prime. It's going to have the same fibre type. And here, this is going to be the set of points of E prime which project down to F pre-image U alpha. And the formula is pretty well automatic. The M prime stays put, and psi alpha is applied to F of M prime and V. And this is another thing that I'm going to leave as an exercise. It's straightforward to check that these define a vector bundle structure on E prime. The base is M prime, the projection is Q prime, and there's some more properties that will follow in a moment. So this is the induced, or possibly the pullback, vector bundle of E across F. And we'll use the Schwick notation. So, properties. First, there's a canonical morphism from the induced vector bundle back down to E. And I'm denoting this by F tilde. This is just a notation that I've used. It's not a standard notation, but it's a reasonable notation to use. And it's simply the projection onto E. And that's certainly fibre-wise a linear map, and it's certainly a smooth map, and everything is fine. That's a good vector bundle morphism over F. The induced vector bundle, of course, is over M prime, and E is over M. So this is the first example of a morphism of vector bundles which does not preserve the base manifold. So here's the general definition. Given two vector bundles, and these are completely arbitrary, E prime, Q prime, M prime, and E, Q, M, this is not a pullback situation. Given any two vector bundles, a morphism from the primed vector bundle to the unprimed consists of two smooth maps, a capital F from E prime to F, and a small f from M prime to M. And these must commute with the bundle projections And as a consequence of that, each m prime gives a restriction of f to a linear map from E prime over M prime to E over Fm prime. That's the definition of a general morphism of vector bundles where we allow the base manifold to vary. So just going back to the top of the slide, F tilde is a morphism of vector bundles over F, and furthermore it's a fiber-wise isomorphism, and that's terminology that explains itself, I hope. That is, for each point of the base of the domain, the restriction to the fibers is an isomorphism. Now, this is worth looking at because any vector bundle morphism over an arbitrary smooth map, which is a fiber-wise isomorphism, will induce an isomorphism of vector bundles from the domain to the induced vector bundle of the target. And if there's time in the course, we'll come back to look at this, because this observation enables us to handle arbitrary morphisms of vector bundles and do quotients and kernels and all the standard things. But that's not now. So, because of this, fiber-wise isomorphisms are sometimes called pullbacks, and again, this is a confusing use of the word, we won't use it. So, here's a question to which the answer I don't think is obvious. What are the sections of an induced vector bundle? So you stare at this for a bit, and the first thing that probably occurs to you is that if you're given a section of the original vector bundle, then you can sort of pull the section back to a section of the pullback bundle in a natural way by this formula. Okay. Roughly speaking, mu prime is mu comp f. So f is going from m prime to m, and mu is going up to e. Okay, so the composite would actually go from m prime into e, but we're keeping track of the base point so that it is actually a genuine section of the induced vector bundle. And that's often called the pullback section. Again, I'll avoid that word. We'll call it the induced section. And there's another terminology coming later. Mu shriek. So that's a good start. Now, for any function on M, that's the target manifold, U mu shriek is U comp F by mu shriek. And that really just follows immediately from this diagram I've written down on the side there. However, if I take an induced section and I multiply it by a function on M prime, a U prime smooth function on M prime, then assuming that it's not of the form U comp F, it'll give a section of the induced vector bundle that's not an induced section. And this is how we get arbitrary sections of the induced vector bundle. So forming finite sums of these things, ui prime times mu shriek I, where the ui primes are smooth functions on M prime, and the mu I, of course, the sections of E, gives every element of this tensor product. And this is going to be the answer. But first, let's just look at what this means. It's a tensor product of modules over the algebra of smooth functions on M. And the tensor product, let's skip to the bottom of the slide. the tensor product essentially means that if we've got a tensor product of a function on m prime and a I beg your pardon, a section of E, and if we multiply that section of E by a function on M, then we can move that function across the tensor product as long as we take its composition with F. So that's the rule for working with these things, but it comes from the following observation. Gamma E, I'm over here, gamma E is a module over smooth functions on M. That's straightforward. Next, smooth functions on M prime can also be made into a module over C infinity M. Simply by defining the module multiplication of a U prime by a U to be U prime times U comp F. Now this is something that would be a bit peculiar if we just met it out of context, but it enables us to make rigorous this shifting across the tensor product here. So the meaning of the tensor product over smooth functions on M is this equation here, equation 122. So here's the theorem. We form this tensor product. Remember, we've started off with a vector bundle and a smooth map for which the target is the base manifold of the vector bundle. We've formed the induced vector bundle and we're asking what the sections are, the module of sections. So this map from this tensor product that sends a tensor, a basic tensor like that, to simply the product of U prime, function on M prime, by the induced or pullback section. That map, extended to finite sums, is an isomorphism of modules. So we have that the module of sections of the induced vector bundle is isomorphic to this tensor product. There's yet another way to write things. Let 1 denote the function on M prime rather, which is constant at 1. Then this map up here, 123, this map sends one tensor mu to mu shriek, the induced section. So given that that map 123 is an isomorphism, we can identify the induced section with the tensor product 1 tensor mu. And this is quite a useful way of working, depending really on how your mind works and what your background is. 1 tensor mu can be used as an alternative notation for the induced section. And this remark here I've actually already made. The induced section could also be regarded as the composite mu comp F. This is a bit of an abuse of notation, but it's essentially true, and it does occur in the literature. You may meet it. So, final comment, and this is more or less standard when we meet these finite sums. For many purposes involving sections of induced vector bundles, it's sufficient just to consider sections of the form U prime tensor mu. So, finally back to product manifolds. So, at the beginning we had two manifolds, M1 cross M2, and I defined the product manifold structure on the set, M1 cross M2, and I posed the question of what the vector fields on the product manifold are. So this is how to do it. We form the product manifold, of course, and we've got these two projections to the first factor and to the second factor, and I form the induced vector bundles for both of them. I take the tangent bundle to M1 and pull it back to M1 cross M2, and I do the same thing with Tm2 using the second projection. So I've now got two vector bundles on M1 cross M2. I take their Whitney sum, there it is. Okay. There's a natural map from this to the tangent bundle of M1 cross M2. It's smooth, that's easy to check, over each point of the product base, product of the manifolds. It's an isomorphism of vector spaces. So it is in fact an isomorphism of vector bundles. In other words, T of M1 cross M2 is isomorphic to, let's just call that xi for brevity. Okay, and therefore the module of sections is isomorphic to the module of sections of xi, and therefore the module of vector fields on M1 cross M2 is isomorphic to the module of sections of this thing, xi, and that breaks down into the module of sections of the induced vector bundle and the module of sections for M2, and you look at either one of these, you know now what to do. We take vector fields on M1, we pull them back to the product manifold, and we take finite sums. And that's how we arrive at an explicit description of the vector fields on the product manifold. And you may think that's quite a lot of work. If you do, well, I agree. It's quite a cumbersome construction, but it does actually give you an isomorphism, an explicit description of this module of vector fields, which is what you want. Of course, in any given situation, you may be content to work with vector fields of a particular type, and of course that's fine. But if you do need the general result, then this is it. Okay, there'll be more about vector bundles, and indeed we'll come back to induced vector bundles also, assuming there's time. And what comes next will be a different topic.